The universe is a place of unfathomable scale and wonder. Some stars dwarf our Sun, some planets possess masses rivaling small stars, and colossal black holes anchor entire galaxies that spiral around them. In this cosmic arena, these behemoths constantly challenge our imagination. If the thought of endless voids and towering celestial bodies unset you, these grand spectacles may truly send a chill down your spine. Fasten your seat belts as we explore these awe-inspiring giants one by one. It is a long story, so let us drift into the world of dreams together. But before we begin, don't forget to like and share. Unlike any planet in our own solar system, WASP-17b is both incredibly massive and strangely light. This gas giant has nearly twice the diameter of Jupiter, yet only about half its mass, making it one of the lowest density planets ever discovered. Scientists call it a puffy planet because its atmosphere is bloated far beyond the typical range of gas giants. Located about 1,300 light-years away in the constellation Scorpius, it was discovered in 2009 via the transit method, detecting the subtle dip in a star's brightness as a planet passes in front of it. The data showed that WASP-17b was far too large for its mass, raising immediate questions about its existence. Usually, a planet's size and mass dictate its density. The larger it is, the more mass it needs to hold itself together under gravity. WASP-17b's low density suggests an atmosphere that is extremely extended, making the planet appear much larger than its solid core. While not fully understood, astronomers suspect this puffiness is due to tidal heating and its proximity to its host star. Orbiting at a blistering distance with a period of only 3.7 days, its atmosphere is superheated to over 1,500 degrees Celsius, causing it to expand like a hot air balloon. This intense heat likely prevents the planet from contracting into a denser form and may even be stripping its outer layers away into space. Furthermore, WASP-17b travels in a retrograde orbit, meaning it moves in the opposite direction of its star's rotation, suggesting a violent past involving a gravitational encounter with another massive body. In 1987, a flash of light reached Earth that allowed astronomers to study a supernova in unprecedented detail. SN 1987A wasn't just another explosion in a distant galaxy, it was close enough, only 168,000 light-years away in the Large Magellanic Cloud, to provide data that fundamentally changed our understanding of how massive stars die. The progenitor was a blue supergiant, Sanjulic-69202, a star 18 times the mass of the Sun. When its core ran out of fuel and collapsed, a shock wave tore through its outer layers, releasing staggering energy in seconds. One of the most groundbreaking discoveries was the detection of neutrinos. These ghost particles reached Earth's underground detectors before the light did, confirming their critical role in the mechanics of stellar collapse. This event forced scientists to rethink the evolutionary paths of massive stars, as blue supergiants were not previously seen as primary supernova candidates. Decades later, telescopes like the Hubble and JWST continue to track its remnants, revealing a striking triple ring structure of glowing gas. These rings were likely shed by the star thousands of years before the explosion. As the supernova's shock wave slams into these rings, they light up, allowing us to study the long-term impact of the explosion on the interstellar medium. Closer to home, Jupiter reigns as the undisputed king of our solar system. A gas giant with no solid surface, it is composed primarily of hydrogen and helium, much like the Sun. With a diameter of 143,000 kilometers, it could swallow 1,300 Earths. Jupiter is so massive that if it had been about 80 times heavier, it might have ignited nuclear fusion to become a star itself, leading to its nickname as a failed star. Its gravity has acted as a cosmic gatekeeper, often deflecting comets and asteroids away from the inner planets, though sometimes redirecting them toward us. Its atmosphere is a chaotic realm of ammonia ice clouds stretched into colorful bands by winds reaching 600 kilometers per hour. The most famous feature is the Great Red Spot, a high-pressure storm that has raged for centuries. Beneath the clouds, the pressure is so intense that hydrogen turns into a liquid metallic state, which conducts electricity and drives Jupiter's massive magnetic field, the strongest in the solar system. Jupiter is a system unto itself, with 95 known moons. Including the 4 Galilean moons, volcanic Io, icy Europa with its subsurface ocean, the magnetic Ganymede, and ancient, cratered Callisto. Finally, we look to the Sun, the heart of our solar system. A churning ball of hot plasma, it provides the energy that drives every biological and geological process on Earth. At its core, temperatures reach 15 million degrees Celsius, providing enough energy for hydrogen nuclei to overcome electrical repulsion and fuse into helium. This energy travels for hundreds of thousands of years through the radiative and convective zones before escaping the photosphere. Beyond the visible surface lies the corona, an outer atmosphere that is mysteriously hotter than the surface itself, stretching millions of kilometers into space as the solar wind. The Sun follows an 11-year cycle of activity, marked by sunspots and explosive solar flares that can disrupt our modern technology. Currently in the middle of its life, the Sun has about 5 billion years of fuel left. Eventually, it will expand into a red giant, potentially engulfing Mercury, Venus, and even Earth, before shedding its layers to leave behind a white dwarf, a dense, cooling ember that will shine for trillions of years. While our Sun is not the largest star, it serves as the essential yardstick for our understanding of the cosmos. Smaller, cooler red dwarfs sit at one end of the spectrum, while hot blue giants and massive red supergiants define the other. Among these, the scale of hypergiants is truly beyond belief. In the constellation of Orion, about 1,400 light-years away, we find WASP-12b, a gas giant so close to its host star that it is literally being pulled apart. Orbiting in just 1.1 days, its proximity causes atmospheric temperatures to exceed 2,500 degrees Celsius, tearing molecules apart. Under the relentless tidal pull, the planet has been stretched into a teardrop shape, with its outer layers constantly siphoning off into space. This dark world absorbs over 90% of the light that hits it, likely because it is too hot for reflective clouds to form. Its fate is sealed. Within a few million years, it will either shrink into a rocky remnant or be completely consumed by its star. Another milestone in exoplanet research is HD 209458b, nicknamed Osiris. Located 159 light-years away in Pegasus, it was the first planet discovered using the transit method in 1999. Osiris proved that we could not only find distant worlds but also measure their size and probe their atmospheres. Observations revealed high-altitude winds screaming at thousands of miles per hour, driven by the extreme temperature difference between the side facing the star and the side in eternal darkness. It was the first planet where water vapor, carbon, and oxygen were detected in the atmosphere, laying the foundation for our search for life-sustaining molecules like oxygen and methane on other worlds. When we look at the stars themselves, few are as famous as Betelgeuse in the constellation Orion. A red supergiant in the final stages of its life, it is roughly 700 times the size of our Sun. If placed at the center of our solar system, it would extend past the orbit of Mars. In late 2019, Betelgeuse famously dimmed, leading to speculation of an imminent supernova. We now know it likely coughed up a massive cloud of dust that temporarily blocked its light. Despite the false alarm, Betelgeuse will eventually explode as a supernova, becoming as bright as the full moon and visible even during the day. Even larger is VY Canis Majoris, a hypergiant so vast that its diameter is estimated at 1,500 times that of the Sun. Placed in our solar system, its surface would reach the orbit of Saturn. It is an unstable monster, shedding mass through gargantuan convection cells that create asymmetrical clouds of dust and gas. These dying giants are the factories of the universe, enriching space with carbon, oxygen, and iron, the building blocks for future stars and planets. Similar titans include NML Cygni, shrouded in thick dust, and VX Sagittarii, which pulsates irregularly, expanding and contracting between 1,000 and 2,000 times the Sun's radius. Theoretical civilizations might one day harness such immense power using a Dyson swarm, a vast network of satellites and collectors orbiting the star to capture its energy. Building such a structure around a hypergiant like VY Canis Majoris would require dismantling entire moons or asteroids for material. While purely speculative, searching for the infrared signatures of these structures remains a serious pursuit in the search for extraterrestrial intelligence. In the wake of stellar death, we find the Crab Nebula pulsar. Formed from a supernova recorded by Chinese astronomers in 1054 AD, this neutron star is only 25 kilometers wide but more massive than the Sun. It spins 30 times per second, lashing the nebula with beams of radiation across the entire electromagnetic spectrum. It serves as a natural laboratory, its precise pulses allowing us to test general relativity and study matter at densities where a single cubic centimeter weighs billions of tons. Finally, we encounter the true heavyweights of the universe, supermassive black holes. Ton 618 is a quasar powered by a black hole estimated at 66 billion times the mass of the Sun, one of the largest ever measured. Its accretion disk shines with the light of 100 trillion stars, visible across 10 billion light-years. In the galaxy Halmberg 15A, another 40 billion solar mass black hole has shaped its host galaxy by literally tossing stars out of the central region. These giants reside in galaxies like IC 1101, a monster elliptical galaxy spanning 6 million light-years, roughly 60 times the diameter of our Milky Way. As giant elliptical galaxies, these behemoths have spent billions of years consuming their neighbors, forming a smooth, massive population of stars with little internal structure. Their yellowish hue indicates an aging stellar population where star formation has largely ground to a halt. At their centers, black holes with masses equivalent to billions of suns almost certainly reside. The total number of stars in such a galaxy can reach into the tens of trillions. Their outer edges bleed into intergalactic space, making their boundaries nearly impossible to define. A massive halo of dark matter supports the high-velocity orbits of their outermost stars. IC 1101 represents the ultimate form of these old guard monsters, born from the peak era of galactic mergers. Similarly, S0146-5 is a giant elliptical galaxy in the local universe, dominating its region with a mass of tens of trillions of suns. Like other typical ellipticals, it grew through a long history of mergers, dominated now by elderly stars. Its surrounding hot X-ray gas and numerous globular clusters tell the story of a violent past. This is the likely future of our own Milky Way. When we merge with Andromeda in about 4.5 billion years, we will eventually settle into a similar giant elliptical form. M87, located in the Virgo cluster, is another local giant spanning 120,000 light-years. In 2019, the Event Horizon Telescope provided the first ever direct image of its central black hole, M87*, a 6.5 billion solar mass giant. The golden ring of light surrounding the black hole's shadow confirmed the predictions of general relativity. Its relativistic jet, ejected at nearly the speed of light, is a magnificent testament to the interaction between black hole magnetic fields and accretion flows. Modern cosmology has discovered that the Milky Way, the local group, and even the Virgo supercluster are racing at 600 km per second toward an invisible concentration of mass known as the Great Attractor. Located behind the zone of avoidance where the gas and dust of our own galaxy hide the view, it is likely a massive collection of galaxy clusters and dark matter. It is part of the Laniakea supercluster, a vast gravitational network that shapes the large-scale flow of the local universe. Nearby, the antennae galaxies, NGC 4038 and 4039, show us the drama of a galactic collision in real time. Long tidal tails, resembling insect antennae, have been pulled out by gravitational forces. While the stars themselves do not collide, the compression of gas clouds triggers intense starbursts, creating thousands of new star clusters. This process prefigures the future of the Milky Way and Andromeda, which will eventually merge into a single elliptical galaxy, their central black holes releasing powerful gravitational waves as they unite. The Coma cluster, 320 million light-years away, contains thousands of galaxies. Its center is dominated by two giants, NGC 4889 and NGC 4874, each harboring billion solar mass black holes. The cluster is filled with hot, X-ray emitting gas that would fly apart without the immense gravitational pull of dark matter, one of the strongest pieces of evidence for its existence. In these high-density environments, galaxies lose their cold gas to the hot surroundings, leaving them as red and dead ellipticals. On an even larger scale, the universe appears as a cosmic web. Between the filaments of galaxies lie vast voids. The Boötes void is one of the most famous, a nearly empty expanse 330 million light-years across. While it should contain tens of thousands of galaxies based on average density, we find only a few dozen. These isolated galaxies evolve in solitude, potentially retaining more primordial gas than those in crowded clusters. The Sloan Great Wall, identified in 2003, is a massive filament 1.38 billion light-years long. It challenges our understanding of cosmic uniformity at large scales and pushes the theoretical limits of how large a structure can grow. The observable universe is defined by the age of the cosmos and the speed of light. While the oldest light comes from 13.8 billion years ago, the expansion of space means the current radius of our observable bubble is about 460 billion light-years. This is not a static map, space is stretching, and galaxies are moving. The cosmic microwave background, CMB, marks the limit of our sight, the point where the early universe was opaque to light. The tiny fluctuations in the CMB are the blueprint for the entire cosmic web we see today. Beyond this horizon, the universe likely continues forever, but we will never see it. Due to dark energy and the accelerating expansion of space, more and more galaxies are slipping over the horizon. Once they cross, their light can never reach us again. The universe is slowly erasing itself from our view. Eventually, only our local group of galaxies will remain visible, leaving future observers on a dark island in an empty void. To understand these processes, supercomputers run simulations like the Millennium Simulation, Illustris TNG, and Eagle. These projects track the evolution of the universe from the Big Bang to the present, modeling dark matter, gas, star formation, and black hole feedback. These virtual universes allow us to test the laws of physics and predict the gravitational wave signals of black hole mergers. In this grand narrative, dark matter is the silent architect. It does not shine or interact with light, yet it is the scaffolding upon which all galaxies are built. Long after the last stars fade, dark matter will remain an invisible skeleton spanning the graveyard of the universe. While we do not yet know its true nature, its persistence is key. If dark matter does not decay, it will maintain the structure of the cosmos even when only black holes and cold remnants remain. Some speculate that in the far future, exotic forms of life might even find a way to tap into the energy of dark matter, though this remains purely in the realm of imagination. The observable universe is a shrinking island of light in a vast sea of darkness. The graveyard of invisible galaxies beyond our horizon reminds us that everything has an end, even if the finale is hidden from our eyes. That concludes our journey through the wonders and the mysteries of the cosmos. May your dreams be as vast as the universe, and may you have a wonderful day ahead. We will see you in the next episode.